Everyone, this video is about this important application spring maths problem. This is standard application of second order linear differential equation. So there we're going to consider three different situations. The first one is the simplest one. So suppose there is a ceiling there and a spring is here. So it has its own stiffness and it has its own constant. This K represent the stiffness of this one, and you will see how this one kicks in. And this is called the natural length. So this is where we set y equals 0. So we represent this thing as its natural length. Now I think its gravity is pulling this the entire spring itself a little bit, but the stiffness is very strong, so the gravity doesn't really affect its natural length here. Now there's nothing attached at the end, and there's something called Hooke's law. It states the following: if you push it this way, or if you stretch the spring downwards, the spring will generate a force. And Hooke's law says the force, here's a force generated by the spring when you try to push this way or that way, is given by the following formula. The formula is K times Y. Y is this position, and this way is the direction of a positive direction, and this way is negative direction. That's kind of opposite of usually how we look at the Y values, but that's the setup we're going to use. And importantly, there is this negative. For example, if Y is a positive value, and if it is stretched like this, let me use a picture down here. This is our natural length, y equals 0. Suppose we stretched it so that the endpoint here is somewhere in a positive value. Let's say that's y equals y1 here. Then it's conceivable that the spring will generate a force to return to this position y equals 0. So that's why there's negative when y, the end position of this spring, is a positive. The force is actually backwards, the opposite of the sign of the position y. And this K is related to the stiffness and material that was used to generate the spring and so on. Or if it is contracted to this position here, like this, in that case that will be the position y equals y2. Then y2 here, according to that setup, y2 is a negative number. The force is generated at that point by the spring system is this way. It's going to push it away, so that's positive direction. Force is going that way, but y is a negative value, so it's opposite sign is the right thing. So this is often summarized as the force to return to this natural length position is proportional to its displacement. So here you can state as a force to return to the position y equals 0 is proportional to its displacement y. So that is one source of force. Another thing is that what we are about to do is we're going to attach a mesh at the end of the spring here, like this. We're going to attach a spring. Then there is the force generated by the spring system, and there is a force generated by gravity. So I'm going to write Fg, the force generated by gravity, and this is as long as we stay close to the surface of the Earth, we assume this is almost constant. There's always m times g. G is the gravitational constant on the surface of the Earth, and m is the mass of this object. That's the second source of the force. And another one is that eventually we're going to be looking at situation, this mass and the spring, once it begin to move and this kind of interact each other. So you will be looking at motion of this mass going up and down. And as we do that, if the medium of the space here is air, then we can think about air drag, air resistance. Or if the medium is a liquid, that creates a more serious drag, so there's a drag force involved. If the medium is more complicated, it's different, then principle might be different, but usually physicists set up this drag force, we're going to call here is just an air drag, but it could be liquid drag if it is happening inside the water, the drag force is stronger. But the general principle is that this force is acting against its direction of a velocity, y prime. In this one-dimensional motion, y prime with the sign built in is a direction, so it's opposite direction it's acting on. And there is a constant involved, so that constant, just like a k here, spring constant, there's this drag constant in here, a is involved. In this case or that case, both cases, k is considered as a positive constant, and we're using this negative sign out there to built in. A is also positive constant, and this is the speed. If it's moving, for example, this direction, I guess the y prime here is a negative. If this is the velocity, like that, and then that's the velocity vector, and here's a force vector, Fa, is this force is because it's moving toward to that direction, air drag is acting against it like this. This is the action-reaction between the mass and the air molecule, or whatever the source of the material that causes this drag force is the opposite this way. So if y is going to that direction, air is going to cause different opposite reaction there. So that's why there's negative there. So these are the main three sources of force that is acting on this mass here, this is definitely what we are going to be looking at. Now let's review the Newton's second law of motion, which connects our intuition about the forces with the acceleration. If y is a position, the second derivative is acceleration, and this is related like this: m times the mass that we're looking at attached to spring, and how fast it's moving is related to how much the force is exerted, net force in here. So there are three sources of forces there, which is the first one was the spring force, Fs there, using Hooke's law. We're using the Hooke's law, and which, as far as I know, that is based on experimental result. So the Hooke's law, and there's a gravity is acting on that, and there's air drag is acting on that. These three forces are acting on this mass there. Adjust it a little bit. The law states that if we exert certain amount of force, and if m is pretty heavy, then acceleration you will observe is relatively small. If this is, let's say, 5, and that's 5, then this will be only 1. We're exerting the same amount of force, 5 here, but if the mass is just 1, then acceleration is 5. So if you push with the same amount, if it's lighter, then it's move faster. That's what this principle says. And this phenomenon is true. That part's puzzling and something you have to think about. If there's no gravity, this one is still true. In space, nothing is pulling or anything, there's this object m. If you exert a certain amount of force, then this will be still happening. So with the gravity out of the picture, it's very counterintuitive. So it's actually a serious thought experiment you have to go through to believe this statement that is happening in space with no gravity in there. Right? But right now, then we accept Newton's second law of motion, and that net force of three different sources of force are like this. So originally I planned to consider a simpler case, but I will just consider this case here, and all in general consider the situation about this air drags and kind of derive the simpler cases from there. So we use this Newton's second law of motion, m times y double prime equals Hooke's law was about negative k times y is the force to return to this natural position there, and gravitational force was just mg, remember, and air drag was working opposite way to this velocity wherever it's going, and there's some constant involved in there. So this is the equation. We generally write this in terms of left-hand side in operational form, and we keep the constant in front of constant y double prime 1. So we will divide first. Y double prime equals negative k over m, y plus m divided there, and a over m y prime. So this is the equation, and you can see this part's constants that will stay on the right hand side. So if you move everything to the left hand side, that has y in it, and I will write this am y prime first, that's the first order, and no derivative part is written like this, is equal to g. So that part here is the differential equation you want to solve, and this is the second order differential equation with a constant coefficient and right hand side. That phi here is fairly simple, which is just constant. So let us write this one as a operational term. It's a d squared and a over m d plus k over m operator I with I acting on it, and here's a g. So let's look at that, and because it's the second order and with a constant coefficient, it's completely classified by when we complete the square. So if you complete the square, it's a d plus a over 2m is I squared, plus if you complete the square, it's going to be the following. I think it's a 4m squares down there. It's 4m squared. I think there's a 4k. I think there's a 4km, right? So that there's m in there. It's minus. This is a squared divided by 4m squared. So that's going to be just a squared and I in there. So that's the operator of this part in here. So that's, I'm going to write it as L here. That's our operator. It completes the square form like this. From there, we can determine it has a complex solution and everything. So let's look at the first case here, where we know if this is a positive or negative, it has this different shape of the solution. The case that if this is a positive case in here, so that means if you look at just the numerator, since this part is a positive, 4km minus a squared being negative. If that's the case, I'm sorry, it's positive. This is a case is a positive, is the complex case. Let's think about the meaning of this one here, 4km minus a squared. That's actually the discriminant, pretty much. This is the case that, when it's going to be positive, is that this part is the mass, and the k came from the spring constant, and this a came from the air drag, without knowing much about how these constants really represent. But if we just simply assume that air drag is very, very small, so that if you assume a is relatively small, and then you can imagine that stiff spring here, and air drag is very, very small. So this is probably, most of the cases, this is a positive. But you can imagine very light mass, and spring constant is very, very weak. It's a very, very tiny wire it may have made out of, and relatively, and if you put that into a water, then the drag force is relatively very strong. In that case, you can imagine that this being negative. If that's negative, then it's going to have a real solution, so that's different. But if we're looking at a very stiff spring system, and with air drag we expect it's very small, this is most of the case, is the case in there. So if that's the case, we know the solution look like this. This is because this is positive, it's a complex solution. So it's a y look like, and e to the the negative of that number is negative a over 2m t times the cosine of omega, because it's kind of bulky, I'm going to write it like this, omega t, plus the same exponential part, and times the sine omega t is how it's going to show up. Plus, we have to, this is only the homogeneous solution, the kernel part, so we have to add the special solution, y0, I'm going to say, or f0. I'll write f0 here like this. Turns out this case f0 is fairly simple. So let's think about what this f0 is. You look at it here, you have to figure out a function such that if you plug it in here, it gives you a constant. Constant is a kind of polynomial. I hope you had a chance to do this type of thing in your guessing exercise. If you plug in constant in here, that's going to be 0 because if you differentiate it here, differentiate a second time, that's a 0 again. So we can just match this constant in there. So what could be this constant in here such that it becomes this constant g? You have to cancel m. So I'm going to write it over here. So f0 is to cancel m there. So that these two cancel. There's no g, so you've got to put that g in there. And there's no k in there, so we have to divide by k. So this mg over k, right, this mg over k is the particular solution. That the solution is not coming from homogeneous equation. Okay, so this particular solution plus the homogeneous equation is the shape of the general solution, and I forgot to put C1 and C2 in there. These are the coefficients. So with this initial condition, and where is the initial location, and where is the initial velocity we're about to release, that will determine these two coefficients. In general, it looks like this if we have very, very small, relatively small air drag involved, and that's the shape of the solution. So let me do a little bit of algebra in here to reshape this solution and understand this important property involved in this the system there. So I'm going to draw a line right there. I'm going to look at this general shape and do some algebra. Is that general solution y has this common factor, which is e to the, it's really a negative number, not just the negative symbol, because a and 2m, these are positive numbers. So we have this decaying factor, right? It makes everything decay because it's not fast growing function, and c1 of cosine omega t and c2 sine omega t, right? Plus out there, you write it over here, plus out there is a plus mg over k, and that's the constant part. So what happened really is this is not changing very much. That you can probably understand because constant and cosine and sine, this is absolutely bounded function, and then this is going to kind of kill the magnitude of all that, and you can easily see from here eventually as t is increasing that this one is going to be disappearing, become almost this mg over k. So this is where the mass is settling onto. So that's the usually term they use in equilibrium position. So without doing any algebra, we already see that this is going to be the equilibrium position. That's going to where it's going to settle on. And this part is oscillating part. But we're going to do a little bit more rigorous calculation than just it's decaying down to about this oscillating part. Here's how that usually the usual technique is the following. Because it's a bit bulky here, let me just separate this part and C1. What we're going about to do is just about this part inside the parentheses and leaving that part outside. Here's a C2 and sine omega t. Right, let me change the thickness a little bit. So there's a nice way to simplify this one. We can realize the C1 and C2 of a cosine and sine value of the same angle. To do that, it must be a number whose square add up to 1. So for that, the following is the technique. If you pull out this C1 squared, C2 squared, so about the small size, and you put it in the C1 there, and root C1 squared, C2 squared, and cosine omega t plus there's a C2 and root C1 squared, C2 squared. If you pull out that much, it'll make these two quantity whose square of these, sum of the square of these two terms is going to be exactly 1, and that's the a motivation of this technique. Let me show this a little bit over here. All right. And we'll continue down here and the following. So I'm going to call that x part because of this I think is supposed to be the y-coordinate, and this is going to be the I was wrong. This part is supposed to be x-coordinate, I think. No, I was wrong. Sorry about that. Y, and here's x-coordinate. So you can easily verify because of that trick we factored out the right amount such that the x squared plus y squared is exactly 1. That's something easily you can verify. If you square it, you have c squared. If you square that part, you have c2 squared. So if you add them up, they cancel because denominator is now c1 squared plus c2 squared. So that puts x and y in the unit circle. Here's the x and y. This is a perfect circle, and there's this radius 1. And this points wherever it is. It's somewhere on this unit circle, like this one in here, somewhere on the unit circle, and that's exactly x comma y that you were looking at there. These are the x-coordinate, and that's the y-coordinate. If it's on the unit circle, you know that x is, if I call that one an theta degree, okay, then x is cosine theta, and y is a sine theta. This well-known parameterization of coordinates on the unit circle. So we can replace this one with a cosine and sine value. Or you can easily say that if anytime if you look at a pair of two numbers whose sum of the square of those two numbers is equal to 1, then it's always can be realized that that's the values of a sine and cosine of the same angle. So let me continue over here. Therefore, we have achieved following that over there, that C1, let me just write it like this. That part becomes, we have this magnitude of a C1 squared, C2 squared, and let me write it, this part, when we write this part first, and the sine omega t times this part is now cosine theta. So we can write it as a cosine theta. Plus that part has a sine theta in there, sine theta, and cosine omega t. It's a cosine omega t. All right, that's how this inside of that part changes. Then I hope you recognize this as the addition formula of the sine. So, and this is something that you should remember to be able to understand this. If you look up the addition formula of a sine, that's exactly this one. If you have omega t plus theta in there, and then if you unfold this one using the addition formula, it falls out exactly like that. So that this juxtaposition of this two wave function right here can be simplified nicely into this sine omega t plus theta. The benefit or advantage of looking at this expression in here is that theta is something that completely fixed or determined by the C1 and C2, and that part is also explicitly written like this, and it gives us the sense that what this one really is just a pure wave with shifted left and right little bit with this period factor in there. So from there you can easily see that it has frequency, it has a period in there. This phenomenon of a motion that has a frequency and a period, and this type of a dominating part, is the quality that we perceive as a nice sound and a pure tone and something like that. So out of all that, following is an important observation to me. Out of all that, let me write in a different color. There is a Hooke's law, and there is a gravity, there's a drag force involved. Out of all that, somewhat it survived this property of having a frequency and period. This guy survived, so that in many situations in natural phenomenon we have this perception of nice hearing that is coming out of this property that having the frequency. So let me explain this thing in a more physical terms. without entering the perception of hearing anything, and I can demonstrate this amusing part of this motion. So for example, this is where the equilibrium position is. Equilibrium position now is different from y equals 0, the natural length. The equilibrium position here is this mg over k. Remember, this decaying factor takes the entire functional part away, leaving this constant part. So as time goes by and this motion is going up and down, it's kind of settling on to this part in here. But the actual motion is this vertical motion and up and down, right? But I'm just going to use it for here for different type of situation. So it's actually moving it like this, and this is the these three forces that interact each other. These are acting on this mass in here. Out of all these three things acting on that, the following property had survived. What it is that at the beginning we have amplitude here. This amplitude is fixed. So let me write down our final answer here. So about a little disorganized here. But this is the part of the answer. So if we have this answer in here, our original solution, y, that has this exponential part, the negative a over 2m, t multiplied by this c1 and c2 that look different. Now it has an identical expression like this. So we have this constant amplitude part kicks in, and we have pure sine wave with a little bit of shift. That's what that part is doing. Plus, there's equilibrium position mg over k. So that's how it simplifies a little bit. It still looks complicated, but because of the one sine function appearing here, we understand better about this motion. So at the beginning, this amplitude doesn't change, but you can see this part right here is changing, is decaying because it's exponential and negative. So at the beginning, we have maybe this much of amplitude, but a little bit later, after a little bit of a while, you can imagine this amplitude here is a little bit smaller. And a few more seconds later, because of this decaying factor, this moving is getting smaller and smaller, and we use this damped, the word damped, this damped harmonic motion. Amazing part is that if you think about when it crosses this mg over k, this is mg over k, the equilibrium position. So when it's moving this much of oscillation, time it takes to cross this one a couple times, and here if it is moving a smaller oscillation, and you can think about how often it's moving back and forth locally just around the time. If it's moving the smaller oscillation in here, how long it's going to take to going up and down, and that's kind of the idea of the frequency. But that is determined by this part right here. And if you look at mg over k, if you look at the sine curve, and if you look at this curve in here, it actually moves, something like this, and getting smaller and smaller. But if you look at this interval, when this crosses the equilibrium position, these are the time interval. If you measure those, if you look at it here, and if you look at this expression, this is always 2 pi over omega. I think it's a pi over omega. It is half of it. Pi over omega, and pi over omega, and pi over omega. And this is always the same. So there is this phenomenon of constant frequency of period is involved when it crosses this equilibrium position. This is the phenomenon that's very difficult to explain, just word by word or using some sort of principle. This is it's a hard mathematical fact, and which is so important, and it's our everyday experience is governed by this property, sometimes affected by this property, having this same amount and all the time. So at the beginning it oscillates a lot, but time it takes to complete the cycle there is the same as the time it takes to complete that little oscillation cycle in there, and that time happen to be always the same. And that's an interesting phenomenon out of this, even though there's air drags involved in there. So that's actually, this constancy is the mathematical description of nice sound. When there is something like this, the sound's much nicer than irregular crossing, period of crossing time. Now we're back to this this general statement and considering the next case where this part 4k minus this part here is positive. So that was wrong. This is supposed to be negative so that this thing has real roots. It's negative in here. So when is it going to be negative? That means this air drag or drag force of this medium is a lot stronger than the mass times 4 times the spring constant. That's very unlikely, but think about it is the medium of the drag force is not just liquid, it's some sort of jelly or some jello or something. So it's gooey object, so it's very, very strong drag forces involved to create something like this. Then it's going to have a real solution. The shape of the real solution look like this, lambda 1 or 2, whatever that is, and it has this negative a over 2m plus minus square root of that, that's 2m over square root of, now because this guy is negative we have to flip this around as a squared minus 4km is the number involved in there. So this is what you're going to get out of quadratic formula. Here's a plus or minus root of that number in there, so divided by 2m. So important thing to note here is that this lambda 1 and lambda 2 are the real numbers, is in that shape. It turns out both are negative. You can argue definitely by looking at this expression. Here's a negative, and although if it is a negative sign in here, negative, negative, that makes a negative, but even though it's a positive, you can see this inside of here is a smaller than a squared, so this whole thing is going to be smaller than a. So that makes this one positive, or by looking at the sign of this quadratic equation in here, the coefficient of d and coefficient of constant part, both positive, you can easily conclude that the two solutions, the real solution involved in here, both negative. So the shape of the solution this time here is y is e to the negative lambda 1, t, and there's a c1, keep forgetting that part, c2, e to the negative lambda 2. These, sorry about this, lambda is negative, so I have to keep this positive there, and knowing that lambda 1 and lambda 2 are negative numbers, and plus and mg over k is still the particular solution that we're planning here, this mg over k. So let's see. Well, if you think about it intuitively, if there's strong damping force in there, it's going to stop quickly, and it definitely will have equilibrium position, and still you can see because this negative coefficient in front of t in the exponent part is going to make this one as an equilibrium position as well. So it's going to act quickly. But it does not have the sine and cosine, the oscillating factor in there. So if you look at this solution and want to understand what kind of motion it's going to create, and I thought about the various different possibilities. Well, it's all determined by this the pairs, the possibility of the pairs of values c1 and c2. They are determined by the initial position and initial velocities. So so here, by considering these being positive, positive, and negative, negative, and things like that, then one can easily go through, and imagine the following possibilities. So here's a time t, and here's a yt, and initial position above and below this natural length. So actually, let's say this mg over k is a positive number because if the gravity is pulling it down. This is slightly different orientation. Here, up is actually the positive direction, but in actual spring mass orientation, downwards is a positive. So I hope you understand that part. This mg over k is equilibrium position. This is where the natural length position is in different orientation. So let's say if you start from below somewhere, maybe natural length or below length, and it could be the possibility, depending on these initial condition, what could happen to these, the sum of these two exponential part is just simply the damping force is so strong it dies out quickly like this. it doesn't even cross this equilibrium position, it just stops right away. That's one possibility. And another one is that if you contract it beyond this equilibrium position and damping force is so strong, it may die out like this. And if the, for example, initial velocity is 0, you just let that one go, and then there's not much of a momentum involved, therefore it just dies out quickly. Now next case is maybe you can start it here, so it creates a little bit of a momentum, you give a little bit of a push to the direction of equilibrium position, then because of the momentum, damping force is not strong enough at the beginning, it's going to cross it like this, and then Hooke's law is contracting, and in that next case, it's never in all cases on this case that the initial momentum is not strong enough to create two crossing. It's just one crossing and dies out. That's what the formula suggests. If you compute the critical points here, because if it crosses and changes direction, that's where the critical points are. The critical points, if you think about the possibility, there's always only one critical point out of this one if you differentiate and set it equal to 0 from basic one variable calculus technique, and that's one possibility. There's no more two crossing. It's always like that because of damping force. That's an interesting statement. Or if you're contracted above and stretch it, give a little bit of momentum at the beginning, and then damping force at the beginning is not strong enough, so it may crosses like this, but eventually dies out quickly without ever crossing it again. So if you look at possibilities of this one, especially the critical points, then it turns out these are the only motions possible out of this situation with a overdamped, that's what they call overdamped motion. This is the only possibility. Now the remaining case is the following. What if this being exactly 0, so that part disappears, then it has a multiple solution, so a general solution look like this, and C1 equals the negative a over 2m t plus C2, and there's a t kicks in, and negative a over 2m t. And there's a particular solution still the same, mg over k. So this part's clear because of this factor that approaches 0 as t approaches infinity. As time goes, then this one is exponentially decaying. So this part is something you have to think about. This is a decaying factor, but this one is growing. It's a growth factor. So how this is going to settle and which one wins is, I think you have seen this a lot in Calculus 1. If you use L'Hopital's rule, you can easily conclude that altogether exponential decaying force is stronger, so that actually approaches 0 as t approaches infinity. So this one has a very similar phenomenon. If you look at just the curve possibilities of how this one decays down, and it's very similar. And here it's, so I'd like to claim the graph looks a lot like before. So to understand this correctly, let me take a look at this one and think about the critical points. How many critical points can this one have, so that we can still have a statement that it can only cross this equilibrium position only one time. So if you differentiate y prime, differentiate y there, and this one will be 0, and we have exactly the same exponential factor. Therefore, you might agree that if you differentiate this one, you will have exactly like this one with a constant. If you apply the product rule, you have this one shows up with a constant, but t will still survive as we do that. Because all that had 3 terms, and this one has the same exponential factor, so you can write it, if you factor out a over 2mt, it looks just like this alpha times t plus beta, where alpha and beta is written in terms of C1, C2, A, and 2m. So it must look like this. And we want to know when this one is possibly 0. We know this is non-zero, only this can be 0, so this one is going to be 0 in here. So most of the case, probably it will create this, there's this, it gives you the when it crosses, so that crossing will correspond to that. So here's the picture of that graph again, and all these things are still the possibility of that one. And for this special case, they use the word critically damped, I think, critically damped, but it's qualitative. I mean, if you look at the picture, it looks a lot like overdamped motion. So anyway, these are the three cases. Let me show this again. These are the three cases that come out of this situation. Three forces acting together, depending on the drag force is stronger than the spring contraction force, things like that. And we have three different cases. And especially when the air drag is drag force is very small, we have this very nice and oscillating phenomenon with a constant period involved.